Welcome to the SOFiSTiK online documentation. In this video of the Composite Bridge tutorial, we show how to carry out the design checks for composite cross-sections in the ultimate limit state. For this, we will use the module Composite, and I will first give an overview of the supported checks and concepts, and then explain the input, how the checks are carried out, and how they are documented in the report. The concept that may be used to check if a composite cross-section can withstand the acting forces and moments depends on the cross-section class. If the structural steel part of the cross-section is compact or predominantly in tension, then the section can be classified in section class 1 or 2. In this case, the section has enough rotation capacity to allow for a plastic check, where the plastic resistance of the section is compared against the acting forces and moments. If the structural steel part of the cross-section is more slender and subjected to compression stress, it may be classified in section class 3. In this case, the design check can be carried out based on the elastic stresses in the section. If the structural steel part of the section is even more slender, then the section might be classified in section class 4. That means local buckling effects can occur and have to be considered in the design check. Okay, so we have on the one hand plastic check and on the other hand the elastic check, maybe with an extension to consider local buckling effects. Now, module Composite by default evaluates both plastic and elastic check to give the user the full overview, and I would now shortly summarize this concept and how we support them in SOFiSTiK. Okay, so first, plastic check. This is based on the plastic stress distribution in the cross-section. As you can see, this is here, for example, sketched for a positive or for a negative bending moment. And now, based on this plastic stress distribution, the cross-section is classified. If the section is in class 1 or 2, we can go for a plastic check. Else, we have to try an elastic check. Okay, but here we would like to go for the plastic one. So then the first step is that we check the utilization of the shear resistance. If this utilization is below 50%, then we do not have to care about the interaction between bending and shear. So we can directly calculate the plastic resistance of the section based on the plastic stress distribution and compare this resistance against the acting bending moment. If the utilization of the shear resistance, on the other hand, is bigger than 50%, then we have to consider the interaction. And this is done by calculating the bending resistance with a reduced capacity of the web, as sketched here. And this reduction of the web strength depends basically on the shear utilization. Okay, and then we can do the check, respectively calculate the bending utilization as previously by comparing resistance against acting bending moment. Okay, next we will take a look at the elastic check. Here, module Composite offers two options to do it. In the first option, elastic stresses in the section are calculated. Here, the construction process, including effects from creep and shrinkage, are taken into consideration. And the concrete in the section, of course, has no tensile strength, so it cracks if subjected to tensile strains. And now, based on these calculated elastic stresses, the cross-section is classified. If it can be classified in section class 3 and shear buckling is not relevant, then check for the structural steel is done based on van Mises stresses in the section. If the section, on the other hand, is in class 4 and or shear buckling is relevant, then the check for the structural steel will be done by the reduced stress method. Of course, for concrete and reinforcements, the axial stress will also be checked in both cases. So, in this concept, the interaction between shear and axial stress is considered by the van Mises stress. The second option for the elastic check handles this interaction differently. Here, the check has two parts. First, the interaction between bending and shear is checked. If the utilization of the shear resistance is below 50%, the interaction is not relevant, so this check is directly fulfilled. Otherwise, it has explicitly to be checked. This is done with the corresponding interaction formula from Eurocode 3. Second part of the concept is the check of axial stresses. Here, first, the elastic stresses are calculated as previously, and then the cross-section is classified. For sections of class 3, the axial stress check can be directly done with the available stresses. For sections of class 4, the stresses are recalculated using the effective cross-section to consider local buckling effects. Then the check is done in the same way. And if both the axial stress check and the bending shear interaction is okay, then the elastic check is fulfilled. Okay, so much about the background. Now let's take a look at the input and the created report. We will start with option 1. That means the check is done with plastic resistances if possible. And for the elastic check, we use Van Mises stresses, respectively the reduced stress method. So I insert text task, open it, and paste the input that I prepared. Okay, now, as you can see in module Composite, we first define the task to be done, so which design check should be carried out. Here we use ULS for the ultimate limit state. Then we have to select a design element or several elements for the check. Here we choose the design element 1 created previously that represents the left main girder of the bridge. And then we choose among the previously calculated design load cases from the superpositioning the ones that should be checked. You can either directly call them by writing their number, but here I would like to show you a further feature that allows to select all load cases that have been superposed for the ultimate limit state. You can call them by their type, that is here this D in parentheses. And among those load cases, you can also filter to only get those load cases that have been maximized in the superposition for certain forces. Here, for example, I choose only those load cases superposed for My and Vz. Okay, then let's run this input and take a look at the report. In the task definition, you get an overview of the design checks, the check design elements, and load cases. Okay, and then we start with the plastic check. Here you first get an overview table of the plastic check. For every section along the design element, you get the cross-section ID, the acting shear force, then the fully plastic shear resistance, and if decisive, this is the case here, the shear resistance considering shear buckling, and from these values, the shear utilization. Then we have the acting bending moment and the fully plastic bending resistance. And the next column gives the reduced bending resistance for sections where the shear utilization is above 50%, so with reduced strength of the web. But that's here obviously not relevant because the utilizations of the shear are below 50%. Okay, then now we finally get the utilization of the bending resistance. And most important, also the cross-section class, which shows if the plastic check is applicable. Here for this max My load case, this is the case. Over the full length of the girder, we have section class 1. So the plastic check is applicable and, as you can see, also fulfilled. This is also summed up in an overview plot showing the shear utilization and the bending utilization and position of the plastic neutral axis in the cross section. Next comes the overview table for the elastic check. Here again, for each section along the girder, we get for every material in the section the stresses at the decisive position in the section, reduction factors for the reduced stress method if buckling is decisive, the design strength of the material, and the utilization and cross-section class. This is followed by an overview plot of the elastic check that also shows the utilizations and the section class. Finally, we get a table that sums up the plastic and elastic check for this load case. Here you can see that for this load case, the plastic check and the elastic check are both fulfilled and applicable. So the overall check is fulfilled over the whole length of the girder. So a more interesting case is the load case that was superposed to give the minimum bending moment My in each section. Here, for example, this load case 3002. And if we go to the utilization summary, you can see that the plastic check is not applicable at many positions because the section cannot be classified in section class 1 or 2. However, the elastic check is possible and fulfilled, and from the summary of the decisive cross-section class, you can also see which check is decisive for this load case at the individual positions in the girder. This way we can go through all the load cases that have been selected for the check, and in the very end we get an overall summary if the checks could be fulfilled at the selected design elements. Here we have only one, and the selected design load cases. Okay, now you might be interested how the utilizations and the section class are determined in detail. To check this, you can request detailed information at the selected section. Here, for example, we might check a section in the span, so approximately at 8 meters. To do this, we can add an echo command, which governs the amount of output in the report, and request a detailed information for design element 1 at this position. Note that if you do not insert the X position of the design element section exactly, the next valid section will be taken. Okay, now we run this input and check the report. As you can see, now a section for the detail at this requested position has been added. There you first get information about the plastic check, so the position of the plastic center in the section and the corresponding plastic stress distribution, including the summary of tension and compression forces that constitute the plastic bending resistance. Furthermore, the information about the plastic cross-section classification and the determination of the shear resistance. The next table is about the acting design forces in the section. For the design load case, all sub-load cases from the superposition are listed with their contributions and factors. Next, we have the primary effects of creep and shrinkage listed, showing how forces are redistributed between the materials of the cross-section due to creep and shrinkage. Okay, based on the loads from the design load case and the primary effects of creep and shrinkage, the axial and shear stress in the cross-section is calculated, and you can check them in the plots. Finally, you get the information about the elastic cross-section classification based on these stresses, and a table that shows where the decisive elastic utilization occurs for each structural steel element in the cross-section. Now, you might be skeptical if the construction process has been considered correctly in the calculation of the stresses. To check this, you can request a more detailed information by setting the echo option to extreme. So we run this. And as you can see now, plots for the development of the stresses in the section have been added. So we can go to the individual sub-load cases of the design load case and see how the axial and shear stress develop during the construction process. Also, the effects of the live loads and the contribution of primary effects from creep and shrinkage are listed. Okay, that's the first option to do the ultimate limit state design check, but maybe you prefer to use the second option, so treating the interaction between bending and shear by an interaction formula instead of using von Mises stresses, and treating the sections of class 4 by using the effective cross-section instead of applying the reduced stress method. So I will show you now how to apply the second option. For this, I copy the task created previously. The input will remain almost the same. I only will make a modification at one point, and this is the task definition. Here I want to specify that I want a different concept for the ultimate limit state check to be applied. By pressing F1, I can open the manual, respectively command reference, and take a look at the options. Here you can see that there are several specifications available for the ULS task that can be set by the item check. We have been working with the default that is both. That means do the plastic and elastic check and use for the elastic check the first option. So von Mises stress and reduced stress method. Note here that you can also choose to do the ultimate limit state check by only checking elastic stresses if you do not want to make use of the plastic resistance. Okay, but now we want to have the plastic check if applicable and use for the elastic check the second option, so interaction formula for bending, shear interaction, and the effective cross-section for class 4 sections. This can be requested by using the option both to. Okay, now we set this. Run the task. And take a look at the results. Okay, plastic check is the same as previously, so I will skip this. But in the elastic check, you can see now the differences. So the check starts by first checking the interaction between bending and shear by using for sections with shear utilization above 50% the formula from the Eurocode to evaluate if shear has a critical influence on the cross-section resistance. Here you can see that shear utilization is below 50%, so that's not so interesting here. So I would rather go to another log case that's more interesting. Okay, here we have sections with a shear utilization above 50%, and you can see in this case this formula here is evaluated and the utilization is at 75%, so the check is fulfilled. And here in these cases we do not have to check it anyhow because the utilization of the shear is below 50%. Okay, so this girder has no problem with bending shear interaction over the whole length. And we now can go to the axial stress check. Here, for each section along the girder, we have for each material in the section a comparison of the axial stress against the design strength of the material and the corresponding utilization that results from this listed, and of course also the cross-section class. Next, we get a plot that gives an overview of the relevant utilization in this variant of the elastic check, and finally again a summary of the relevant utilizations. So here we see which check has been decisive and why. Okay, now what about the detailed information? So here, for example, for the section of x equals 8 meter, so the plastic stuff we have already seen. But now for the elastic check, we have some further plots. So, short reminder, the interaction formula for bending and shear depends, among other values, on the ratio of the full plastic bending capacity versus the plastic bending capacity of the flanges only. Now, in the detail plot, you can see the corresponding stress distributions for these values. So here a fully plastic one, and here for the flanges only. And then once again, we have the subload cases that constitute the design load case and the corresponding stress distributions. So what I previously claimed is that we are using effective widths for sections of class 4. So, and I would like to demonstrate that. So I select a section where this is the case, here for example at x equals 6 meters. Run the task, and we take a look at the report. Okay, especially I'm interested in the stress distribution in the section, and you can see here that the effective section is used and the parts that buckle are not effective for the axial stress. Note that in this case you also get a table that sums up the effective widths. Okay, that's it about the ultimate limit state design checks. In the next video, we'll proceed with the checks for the serviceability limit state.